Hello everyone, thanks very much for first clicking on this video. I mean, this is really good maths for you, and it's really important maths for you because although it's not on the spec necessarily, it's going to answer quite a few of the why questions about differentiation, where it comes from. Why does, for example, y equals ax to the n give us a derivative of a n x to the power of n minus 1. Why is that? It also helps us explain, or it will explain, not in this video necessarily, but it will help you see kind of what's going on. But why doesn't y equal 2 to the x differentiate, for example, students write this all the time, to 2x minus 1 times x, so old power goes down, reduced power by 1. That doesn't happen when it comes to functions like this. It doesn't happen when you've got y equals sin x. This in fact differentiates to cosx. Why? Well, it all comes down to discovering that this thing here is very specific only for polynomials, so only for when you have x to the power of something, half, 2, minus 5, whatever. This rule only applies for when you have it in the form y equals ax to the n. Now, let's see why that is. So, I'm going to just draw a curve, any curve, and I'm going to define this as y equals f of x. So I've just got a general curve here, okay? Now, normally, when we find the gradient of a straight line, we would say f dash of x, or m, or whatever you want to call it, dy by dx, we would say our gradient is the change in y over the change in x, wouldn't we? So, the problem we have here, though, is that wherever I take a point on our curve, for starters, if I take any 2 points on the curve and use this y2 minus y1 over x2 minus x1 rule, you can see that this line does not match the curve at all. It doesn't describe the curve, does it? Okay? There's one problem. There's also another problem, that it's obvious that the gradient of the curve is not the same uniformly over the curve. I mean, let's have a look. So if I take this point here and I draw the tangent, remember the tangent is going to describe the gradient at every point because it's a line, isn't it? So you can see the line here is kind of flat. If I take a tangent here, it's getting steeper. Take a tangent here, it's getting steeper and steeper and steeper. And so what we're saying is that the gradient is not consistent. So that is why we say that a gradient of a curve has a gradient function, okay? So let's go back to where we were, and let's try and deal with the conundrum, the problem that we've just set out. So we know that f dash of x is normally y2 minus y1 over x2 minus x1. So I'm going to take 2 points on this curve. Let's take this point here at position x. Because y equals f of x, this is going to generate a y value of f of x. This thing here, if I move along a certain distance, delta x, and remember, delta x is saying a small amount of x onwards, so I'm moving a small amount of x to the right. So let's say this is therefore x plus delta x, and as we know, because y equals f of x, we therefore have a corresponding y value of f of x plus delta x. If I draw a straight line between these two, again, as we mentioned earlier, this straight line does not represent this curve, does it? So, as it stands, we could write that f dash of x equals our y2 minus y1, x2 minus x1. So nothing's changed at the moment. We are still saying y1 subtract, y2 subtract y1, and x2 subtract x1, and we end up with f of x plus delta x minus f of x over delta x. But as we've said, this line does not match this curve. It doesn't make sense to identify these 2 points in the curve and say, right, so it follows this pattern, this y2 minus y1, x2 minus x1. We can only find gradients in this form, though, building up this idea of this triangle. Now, how can we make it more accurate? Well, it seems obvious, doesn't it, that we could take a point a little bit closer then on my curve and make delta x, a little bit smaller. And you're right, it's still a straight line, but it still doesn't match that curve. And then I suppose the next thing I could do is zoom in a bit. And we'll pick another point then, a closer point this time. Okay, let's pick this one. Again, our delta x is getting smaller. We still have a straight line though, mirroring or trying to match a curve. So yeah, you guessed it, we're going to have to pick a point closer. Oh, still a line. Closer, still a line. Closer, closer, closer. And every time we do it, we are matching that curve better, but it's still not quite on the curve, is it? But what happens if we could zoom in an infinite amount of times? An infinite amount of times between those 2 points, such that if I keep zooming in, that straight line would match the curve. Because as we know, the curve has an infinite number of points, and therefore if I zoom in an infinite number of times, the distance between these 2 points would be infinitesimally small. So what we're saying is that once I bring these 2 points together, snap them together, make delta x so small that they're virtually on top of each other, what I'm left with is essentially a line, and therefore I can use the y2 minus y1 over x2 minus x1 formula. So what I need to add to this is the limit as delta x tends to 0, and therefore we have it. This is our differentiation from first principles formula. So let's actually use this as an example, and then you'll see what I'm talking about. So here we've got f of x equals x squared. Let's take this one. We know that f dash of x will be 2x, but why? So we'll use our first principles formula then. So here we go, normal stuff, f of x plus delta x, take away f of x over delta x. So we know f of x is x squared. F of x plus delta x then is, since whatever's in here is going to replace our x, whatever's in here is going to replace our x. If this was f of elephants, I'd have elephant squared. So here I've got x plus delta x all squared, which is the same as, if I multiply that out, x squared plus 2x delta x plus delta x all squared. If I then put this into f dash of x, then, so we've got all our ingredients for our recipe, and we're now just putting it all into this thing here. So we have f of x plus delta x is x squared plus 2x delta x plus delta x all squared. Subtract our f of x, which is x squared, all over delta x. And can you see the thing here? So I can't just immediately say, okay, we'll snap the 2 points together. Remember, we've got our curve here, y equals x squared. We've taken 2 points here, and there's our delta x, the small distance between them to tell us the gradient. I can't just snap it together, because if I did, I'd be dividing by 0, because we're saying when delta x is so small, it basically becomes 0, and we know that we can't divide by 0, otherwise all of our nose start bleeding. So first I need to rearrange this thing and tidy it up, get rid of that delta x on the bottom. So we can see that x squared take x squared, that's not a problem, that's gone. 2x delta x over delta x leaves us with 2x. Delta x all squared divided by delta x leaves us with delta x. Therefore, we can now take the limit. We can now say, let's snap these 2 points together and make delta x 0. And lo and behold, we get our predicted 2x. Smiley face. Okay, now, let's see if you can do it by yourself. So let's try, I don't know, x cubed plus 4x. Can you do that by yourself? Something really worth trying, because you know what the answer is going to be. You know you're going to get 3x squared plus 4. Why not try it? And if you want a real challenge, why not try f of x equals ax to the n, which we know will go to a n x to the n minus 1. Why? Try it out. So literally pause the video and try it out. I'll give you 5 seconds to pause it, right? And then I'm going to go for it. So 5, 4, 3, try it out. 2, try it out. Yeah, definitely try it out. 1, okay. Okay, well done for trying. Right, let's see if what you've done is right. I'm sure it will be. So let's go for it. So we use our first principles formula. We have our ingredients. F of x is ax to the n. F of x plus delta x then is ax plus delta x all to the n. Okay? We're now going to put this into our first principles formula. So f dash of x then is the limit as delta x tends to 0 of f of x plus delta x, which is this, subtract our f of x, ax to the n, which is this. And this is all over delta x. Again, we can't divide by delta x straight away. We can't snap this to 0 because this will be divided by 0, and then again all of our noses will bleed and time will stop as we know it. What we can do is start cleaning this up. So a, notice, has nothing to do with delta x. So I can take that out as a factor. I can also start to expand this thing up. Expand this thing out. So let's move that over there. Give me a bit more space. And so here we go, we're back to here. So let's expand this thing out using our binomial formula. So this is n choose 0 x to the n delta x to the 0 plus n choose 1 x to the 1 delta x to the n minus 1. Sorry, this is n minus 1. Duh. This is n minus 1 and this is 1 plus n choose 2 x to the n minus 2 delta x squared plus dot 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 plus, let's do our general, n choose r x to the n minus r delta x to the r plus dot 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 dot. Let's go do our last few terms then. N c n minus 1 x to the 1 delta x to the n minus 1 plus n c n x to the 0 delta x to the n, and then don't forget we still have our minus x to the n term here, so minus x to the n. Sorry, I know it's really condensed. Ooh, this is really bad. Delta x. Don't judge me for this one. Okay. Right. Don't tell anyone in the maths community that I just did this massive fraction. That looks so bad. Okay. So, what can we start doing? We can start simplifying some stuff up. We know that n choose 0 here, we know that that is 1. Type in your calculator if you don't believe me, and how many ways can you pick out of n, how many ways can you pick no ways? Well, you can only pick that one way, okay? So there's our x to the n. Delta x to 0 is 1, so we have x to the n, subtract x to the n, so this thing's gone. Fantastic. Remember, we can't take a limit as delta x tends to 0 yet because we need to get rid of this on the bottom, so that's what I'm doing now. So here we've got n choose 1, x to the n minus 1 times delta x. So delta x over delta x is going to give us x to the n take 1, and our n choose 1 is just going to be n. Again, factorial theory there. n choose 2, this section here, x to the n minus 2, the delta x, one of the delta x is going to cancel, isn't it? So n choose 2, x to the n minus 2, delta x, no squared this time, done, done. Plus our dot dot dot, plus, now we've got our n choose r, x n minus r, delta x, again, just one of the delta x is gone, so we've got r minus 1 there, that's gone, plus dot 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 dot, plus n choose n take 1, x to the 1, delta x, again, n take 1, lots of delta x, divided by delta x is now going to be n take 2. And then our last term, n choose n, x to the 0, delta x to the n take 1. Right, here we go. I now have no delta x's on the bottom, so now I can say, let's snap our 2 points together. Delta x goes to 0, bang, this is gone, bang, this is gone, bang, bang, okay, and all we're left with is a n x to the n minus 1, because we've taken that limit and all these have disappeared. This is 0, this is 0, this is 0, etc. And here we are, we're left with what we wanted. Excellent, thanks very much for joining us, that was great. I really hope that has helped your theory and that you got it right if you tried it by yourself. See you next time.